ME347, Example 5, using displacement thickness for wind tunnel centerline velocity calculation. For a wind tunnel with a square test section, for Part A, derive an expression for the centerline velocity as a function of the uniform inlet velocity, wind tunnel height, and displacement thickness. For Part B, use this result to calculate how much the centerline velocity increases for the Cal Poly wind tunnel under the following conditions: uniform inlet velocity of 160 feet per second, height and width of the test section of 24 inches, and displacement thickness at the exit of 0.1 inches. For this problem, we will assume steady, incompressible flow of air in the wind tunnel. We will also assume that the boundary layers are two-dimensional. Thus, the velocity profile only changes in the streamwise and cross-streamwise directions, and the three-dimensional flow in the corners of the test section has negligible effect. To solve this problem, we need to apply conservation of mass to determine the outlet velocity based on the specified uniform inlet velocity and geometry. Before we begin our analysis, let's look at a schematic diagram of the test section to help us define our control volume. As shown, after the inlet, boundary layers form and grow on all four walls of the test section. Recall that a boundary layer is a thin layer of fluid near the surface where the relative fluid velocity goes from the free stream velocity to zero at the walls due to the no-slip condition. For this case, the free stream velocity is the uniform velocity in the central region of the test section, outside the boundary layer. For our analysis, we define our control volume to include all the air flowing through the test section from the inlet to the outlet. Because we are assuming two-dimensional boundary layers where the three-dimensional flow in the corners is neglected, a two-dimensional slice of this control volume is also shown for the central region of the test section. Next, we apply conservation of mass in integral form to our finite control volume. The first term on the left is 0 for steady flow where no properties, in this case density, change with time. For the second term, we integrate over all the control volume boundaries or control surfaces, which include the inlet flow, the outlet flow, and the four walls. Because there is no flow through the walls, this last term is 0. Finally, because the flow is incompressible, the density can be brought out of the integral and canceled. For the first term, for the uniform inlet velocity, the integral reduces to negative capital U for inflow times h squared. For the second term, for the outlet, we break up the integral into two regions. Note that both of these terms will be positive for outflow. For the first region, we integrate the boundary layer velocity profile over the boundary layer thickness from y equals 0 to delta, and then multiply by the width of the boundary layer, which is 4 times h. This accounts for all four walls of the test section. For the second region, we assume the flow is at a uniform velocity in the center of the test section. Thus, the integral reduces to v subscript CL times total test section cross-sectional area minus the area of the boundary layer region. Note that for both of these terms, we are slightly overestimating the amount of flow in the corners. Next, since we want to get a relationship in terms of the displacement thickness, we recall that it is defined as shown, where we use v subscript CL for the free stream velocity. Expanding this relationship, we get an equation for the integral of the boundary layer velocity profile over the boundary layer thickness. Note that this result demonstrates that the actual flow rate for the boundary layer is equal to the uniform free stream velocity times the actual minus the displacement boundary layer thicknesses. Substituting in this equation and simplifying, we get the desired relationship for the centerline velocity as a function of the uniform inlet velocity, height of the square test section, and displacement thickness. As expected, the centerline velocity increases as the boundary layer grows thicker in the streamwise direction. An alternative way to derive this equation is to start with a simpler version of conservation of mass for an incompressible fluid. In particular, the volumetric flow rate in equals the volumetric flow rate out. Again, since the inlet velocity is uniform, the volumetric flow rate is equal to capital U times the cross-sectional area. For the flow out, we use the definition of the displacement thickness to account for the loss in flow due to the presence of the boundary layer as shown. Simplifying, we get the same answer as before because we are modeling the flow in the corners in the same way as above. Considering one last alternative, for the outlet, we only account for the flow once in each of the corner as shown. This gives a slightly more complicated result that reduces to our previous result when the boundary layer thickness over the test section height is much less than 1. For part B, calculate the centerline velocity for the Cal Poly wind tunnel operating at its maximum velocity. Substituting in values, we get that the velocity increases from 160 to about 163 feet per second for both equations derived above. Thus, there is about a 1.7% increase in velocity. As a final note, I have included a slide to show how the boundary layer thicknesses were estimated for these calculations. In particular, I first calculate the Reynolds number at the end of the test section to be 4.7 million. For this Reynolds number, it is reasonable to assume that the flow is turbulent. Assuming it is turbulent starting at the inlet, which is a less reasonable assumption, I estimate the boundary layer thicknesses using experimentally developed correlations for turbulent flow. For the disturbance thickness, we get about 0.8 inches, and for the displacement thickness, we get about 0.1 inches. These are probably overestimates for the actual flow, which would likely start out as laminar and perhaps not actually transition to turbulent at all. Thus, the 1.7% increase in centerline velocity that we predicted above is a worst-case estimate.